Hi. Hi. Oh, whoa. It's like, wow. Okay. It's like a photo finish. Hi, John. Hi, Maisha. Hi, Lizzie. Hi. Oh, and I see, I was even saying that she even, hello, everyone. Thank you, Lizzie. And I was even saying hello to her. So I'm saying, hi, Lizzie. Hi, Leah. Hi, John. Hi, Jayla. Hi, May. Hi, Maisha. So that's in a different order. That's in order of visuals. That's visuals. Now the chat order. Hi, John. Hi, Maisha. Hi, Curses. Hi, Lizzie. Hi, Maisha. Hi. Hello, Noel. Oh, sorry. Wait, how did I miss Noel? I'm sorry. Oh, because Black Box. Okay. Hello, Noel. Hello, Eric. Hello. Hi, May. Hi. Oh, here we go with that stuff. Okay. Hi. Blah, blah, blah. Oh, hey, Stephanie. And oh, I'm sorry. Special shout out to Stephanie. Can I say, oh, am I going to give something away here? I do believe actually Stephanie was in the waiting room like about 40 minutes ago. I'm just saying, or not literally 40, but I do know that Stephanie was in the waiting room for a long time. I'm just saying. So thank you, Stephanie. Okay. But yes, hi, Maisha. Hi, Alea. And it's not a competition. Hi. Oh, now there we go with the, okay. You all should get multiplayer co-op points for saying hi to each other, I suppose, maybe. Okay, but now it's getting crazy. So now the chat is crazy. Oh, that's funny. Okay, the chat. That's a good way to keep me. Wow. All right. No, Null is now her new name. Oh, well, I can't support that. Okay. Okay. Oh my God, you guys are hilarious. Just accept. Oh yeah. Now I realize that might have been an embarrassing thing for me to say. I'm sorry. I meant it as a compliment, but right. I guess. Okay. Well, cool. I'm excited to have you guys. And I totally apologize, Stephanie. You should submit for points because I shouldn't have called you out for that. I meant it as a compliment, but okay. Okay, we're going to get down to business here. And as oh, okay, cool. Thank you. Okay. And we often get interrupted, like, because the timing of this class is like right when my son comes on, blah. Today, I want to say we might get interrupted, and I apologize in advance, but also I should leave. You can tell me. I should get rolling like now because I may have to leave a little bit. I do have to leave a little bit early, and you're welcome to warn me of that. Oh, wait, someone just came in. You're welcome to warn me when it's 4. I won't consider it rude. I will consider it helpful if like around 4, if you want to tell me to start wrapping it up. Like, I'm not saying we're literally leaving at 4. Like, don't now go plan a haircut or something. I'm not saying we're literally leaving at 4, but you could warn me at 4 to start wrapping it up. And I would like to maybe let us go like 10 minutes early. So, because I think it ends at 4:20. Yeah. Okay. You follow me. So it won't be rude if you let me know when it's 4, and then I won't stop on a dime right then, but I will start trying to make sure we're wrapped up. Now, also, there's one very specific important thing I do want to get done in lecture today. The 2 lectures are a little bit diverged right now, so I want to make sure we're back. Like, slightly different things have been happening in lecture, so I want to make sure they're exactly the same place. So I want you to tell me, okay, this thing that's on the board right now is unfamiliar, I believe, or at least from lecture. It might be familiar from lab, but I'm assuming that the thing right on the board right now is not yet familiar from lecture. Like, it's a place I want to get to today. I need to get to today. Oh, and fine. Oh, sorry. I'm just getting some direct chats here about the homework. Look, thank you. It's okay. Wherever you are on the homework, just keep going. If you haven't finished something, just keep going. Just do the next thing, whatever you're up to in the homework. Like, obviously, I'm behind you guys too. So don't even do with regular homework, with the problem solving homework. Don't worry about lateness. Don't worry about what Google says. Just do the next thing you're up to. If you've already done one and I've said things in lecture to help you, then revise it, blah, blah, blah. I mean this seriously to everybody because I'm behind too. And I'm not even going to be talking about the homework today. We were talking about it, I know. I mean, homework too. I need to talk about something more general today. So yes, I mean, there's a couple of things in the direct chat. Just don't even worry about it. Just get it to me when you can. Like, it will help you. But on the other hand, ironically, with the game turns, I like you to try to be on time just because I think that they're like easier to do quickly and they're more about reflecting in the moment of that day. So even though they're worth fewer points, and even though they're like sillier, try to be on time with those. But okay, anyway, I have to ask you all a question. So I want to try to derive or prove the thing that's on the board right now. Like, again, I don't expect that it's familiar. at least not from lecture, but I want to get to it today in lecture. So I want to ask this thing right here, this, I need you to remind me exactly how far we got in lecture last Wednesday, because I've gotten myself a little bit confused or disoriented. Like I remember we didn't get to all the pages of notes that I had. And I said, you could read them yourselves or whatever. What I want to know is this equation at the bottom of this page. I believe that in lecture last Wednesday with you guys, I was setting up this idea of a collection of phase staggered oscillators. Let me be more specific. This is what I believe I remember, but I want to be as clear about this. I did. Okay, thank you, John. That's totally helpful. And it's not even. I did. Okay. Then thank you, Elizabeth, with an S. Okay. So I got that far. All right. So, okay, great. Perfect. Thank you both. Serious thanks. And to please submit that for participation. Okay, good. So then good. So here's what I'm going to say to all. Perfect then. Thank you. So I'm just going to now slightly refresh or review for all of you, where that's coming from, the thing on the bottom. Remember, we originally were in the middle of homework 2. We were originally on some problem. I think it was F or something, part 1 F, where it said, what if you have X equals A cosine omega t plus 3.5, right? I'm just reminding everybody. There was this arbitrary exercise in the homework where it said, what happens if you take 2 derivatives of y equals A cosine omega t plus 3.5. And we had this long discussion, I think, again, stop me if I'm wrong, but I believe we had this long discussion where my big point was there's nothing special about 3.5. It's just a number. It's a number that's measured in radians. And what I tried to explain to everybody that hopefully you're remembering is that whatever number we stick in there in the parentheses is called ultimately a phase constant. And so again, I'm technically reviewing or refreshing right now. I'm saying something that I think I already said, but I'm just trying to remind you of that. You can stick a number in the parentheses of the cosine function. We can designate that number with a lowercase Greek letter phi or phi, which looks like a theta turned on its side. That number is called the phase constant. And what it represents is a delay or a head start in the cycle of some oscillator, right? So again, just technically reviewing here, we said that, for example, if we have X equals A cosine omega t plus pi over 2, rather than just plus 0, or rather than just having omega t in the argument, if we have cosine of omega t plus pi over 2 radians, then what we're saying is, when we started timing our oscillator, the oscillator was already at pi over 2 radians into its cycle. What does that mean? Well, we said to ourselves, well, there's 2 pi radians in every cycle. That's our memorizer, if anything, to always bring everything back to. There's 2 pi radians in every cycle. So if an oscillator is already at pi over 2 radians with regard to its cycle, then what that means is it's not all the way at the amplitude. That means it's a quarter of the way into its cycle, right? And a cycle means there and back. So a cycle traditionally means start at your maximum amplitude position, as far away from equilibrium as possible, go all the way through equilibrium to amplitude on the other side. That would be a half cycle, right? Going all the way to amplitude on the other side, and then come back to the original amplitude for a full cycle. So just to review or refresh, if something has a phase constant of pi over 2 radians, that means it's already a quarter cycle in to the process when we started our stopwatch. So it would refer to an oscillator that was already at the equilibrium position when we started our stopwatch, rather than being at the amplitude position, right? That's what we said. Now, then we said, and again, I'm just trying to review or refresh us to sort of what's on this page right here. We then said, okay, So you can stick a number in the cosine argument, and you could stick a number of radians, and it refers to a head start or a delay in the cycle. But we said that's like the reason we've been getting away with not doing that for weeks. The reason we've just been saying cosine omega t, like plus 0 for weeks, is that there would be no need to do that. Like that just makes our life more inconvenient. Like we can start our stopwatch wherever we want, so we might as well start it at wherever's the most easy and convenient to time. And it's really easiest to start timing something once it's all the way at an amplitude position, because that's where it's like runs out of speed. It stops temporarily and is getting ready to turn around and come back the other way. So it's like, it's just easiest to start our stopwatch there when the thing's barely moving. And so we wouldn't ever really care. We wouldn't have a need to complicate our lives with a phase constant if we only had one oscillator. And please remember always, like my underlying like implication here, my underlying belief is that physics is only as complicated as it needs to be. Physics is supposed to be as simple as possible a way to understand complicated phenomena. We don't try to make things complicated as much, despite what it looks like. We're trying always to make things as simple as possible. It's just that life is complicated. So we said the phase constant idea is not really necessary or that useful if you have only one oscillator. But then we said, okay, it becomes useful if you have many oscillators. And if they are at different places in their phase, then it becomes like we might start the first oscillator at the most convenient spot. But then if the next oscillator is in a different point in its phase, we're going to need to keep track of that with a phase constant. So then we said, so again, technically I'm still reviewing or refreshing from last time, but I'm just trying to quickly sort of summarize what's on this page right here facing you. And we had a slightly more detailed picture, I think. But we said now, picture. So I'm looking at like number 2 here. It says, consider a horizontal collection of identical vertical oscillators staggered in phase by a constant amount. Okay, that is a mouthful. I mean, that is definitely a mouthful. But what it is, it's a description really of taking a whole bunch of identical vertical oscillators. When I say identical, I mean all same K, all same M, so therefore all same omega. We're going to take a bunch of oscillators that all oscillate at the same rate. We're going to set them up so that they're oscillating along vertical axes, but we're going to spread them out along a horizontal axis, right? This is what we said last time. And again, please stop me if I didn't say this or if I said it too quickly or whatever, or if you have questions about it. But I asked you to consider a bunch of vertical oscillators spread out on a horizontal axis, spread out equidistantly on a horizontal axis. And then I asked you to consider, and here's the key point, consider that they're all identical in every way, even amplitude, maximum displacement from equilibrium, assume is the same for all of them, but time them, set them off at staggered times so that when the first one is at the amplitude position, maybe the next one, for example, is at equilibrium, and the next one is at negative amplitude position, and the next one is, say, at equilibrium. That would be, for example, staggering them by a constant pi/2 step in phase, right? That's what I asked you to do. Now, 2 things about this. Number 1, pi/2, I think, is kind of the easiest one to picture, but there's nothing magical about pi/2. They could be staggered in step by pi/4, pi/8, anything. I just think pi/2 is sort of easy to picture. Number 2, when I'm asking you to do this, it's a mouthful to describe. It's sort of a hard to draw, kind of. But I want you to realize that what I'm asking you to picture is not that obscure. It's actually not that weird. In fact, what I'm asking you to picture, this collection of staggered oscillators, if you really think about it, what I'm asking you to picture is the simplest possible picture or the simplest possible arrangement of multiple oscillators. Wait, let me rephrase that. It's the simplest possible meaning. Someone's here, sorry. It's the simplest possible meaningful way in which you could arrange a collection of oscillators. when I say meaningful, this is what I mean. This is what I'm saying. I'm saying we could do something that seems simpler. We could take like 1,000 vertical oscillators, arrange them all on a horizontal line, and set them all off at exactly the same time. Like certainly we could do that. And certainly that would be even simpler than what I'm saying, right? We could have a whole bunch of oscillators that are all doing literally exactly the same thing at the same time. But if we did that, it would look like this. So it'd be like up, down, right? Like the absolute simplest thing we could do with a collection of oscillators would be not only have them all be in the same frequency, but literally in the same phase, in the same point in their phase, so that when one goes up, they all go up. And when one goes down, they all go down. And when one's at amplitude, they're all at amplitude. We could do that, but there'd be nothing to say about that. There'd be nothing to analyze about that. And there'd be nothing to do with that. Because if we did that, if we took a whole collection of oscillators and arranged them identically like that, then in effect, what we have is just, for all intents and purposes, we just have one enormous, big, long oscillator that's just going up and down, like a jump rope, right? Like there'd be no sense in which we have multiple oscillators then. In other words, it might be multiple oscillators, but it'd be meaningless. We might as well just have a really freaking long piece of metal on a really wide spring. That's all that would be. So I'm saying, for this arrangement that we're considering now, I'm saying if we took a collection of oscillators and arranged them in the simplest possible way that actually took advantage of the fact that we had multiple oscillators, like that, literally the arrangement I'm asking you to consider here, what I'm calling the phase staggered oscillators, if you think about it, it's the simplest way to arrange a bunch of oscillators that actually is using a bunch of oscillators as a bunch, right? What the simplest thing that we're doing is we're saying they're all staggered in phase, but in the simplest way possible, they're all staggered in phase by a constant amount. Now, right, by a constant step. So what we said, and I'm almost done now, like sort of reviewing what we said last time, I'm saying like, well, I'm reminding you, I guess. Sorry. Oh, sorry. Okay. So I'm saying, someone else is here. Sorry. Well, just to, okay, so I'm going to add a page just to remind you of what we did last time. We said, like, I know I did, again, this is technically still review. Hopefully this is clarifying. Hopefully this is not like a waste of your time, but we said, well, right, if we arrange these oscillators and they were all identical and they were on the x-axis, so they all had the same omega, right? Because they all have the same K and the same M. And this is called oscillator one. This is, right, then what we said was, Just looking at the chat. Oh, wait, no, thank you, direct chat person. Hold on, I missed in the example. Wait, I missed. Oh, fair enough. No, thank you. Well, that's okay. That's sort of my handwriting, but okay, yeah. No, and that was very respectful, and you totally, and thank you for paying attention. And you should totally submit that for points. Direct chat person, thank you. No, that was totally respectful. Okay. What I'm trying to say here though is, okay, I'm just trying to, again, I think this is a big enough concept. I'm sort of trying to sort of quickly review it. I'm just trying to say this to everybody. I'm saying that we're picturing this collection of identical but phase staggered oscillators, right? And if you first just picture the example that the phase staggering step is pi over 2, for example, if each one's increasing by pi over 2, then just realize when you're picturing like pi over 2, that what you really mean is that you're increasing the phase by pi over 2 radians per each meter, right? Like in the very first one, there's no phase step at all. It's like like the very zeroth oscillator, which is at the x equals 0 position. It could be described by an equation y sub 0 equals a cosine omega t plus 0. Like it's starting when it starts. It's starting in amplitude. Then the oscillator that's at the x equals 1 position, like the number 1 oscillator, if the edge one was called the 0th oscillator, then that one is starting with a phase constant of 1 times pi over 2. Then the very next one, now here's like what John said, I remember in general chat last time, like as John pointed out, if any given oscillator we look at, if we're measuring where it is in phase relative to the 0th one, right? If they're all if all the phases are being based on that 0th one, and this was a point that John made, and it's correct, then like the oscillator that is at position x equals 2, in other words, the number 2 oscillator, it could be described by the equation y sub 2 equals a cosine omega t plus 2 times pi over 2. That is, it's pi over 2 delayed compared to its neighbor, but its neighbor is pi over 2 delayed compared to the very 0th one. So the number 2 one is 2 pi over 2 delayed compared to the 0th one. In English, what does that mean? It means when the 0th one was at the amplitude position, then the next one's at equilibrium position, and the next one is at negative amplitude position. It's like 2/4 of a cycle behind the very 0th one, right? So each oscillator in this horizontal line has a phase constant that is like bigger and bigger, as we get farther and farther along. In other words, pi over 2 in this example, what I'm really trying to say is, in this example, pi over 2 is like a step. It's not that phi equals pi over 2. It's not pi over 2 radians. It's pi over 2 radians per every meter that we advance along this chain. For every meter that we walk this way, for every next oscillator we look at, there's an additional pi over 2 in phase. Pi over 2 radians per meter is like the step by which it's like the constant amount by which we're increasing phase as we walk along the x-axis. Really what we said last time, and I'll just say this, it's like a slope. If you were to make a graph in your mind with x as the x-axis, but with phase, phi, on the vertical axis, the graph would be a straight line. For every 1 meter that we walk over, we increase the phase by a certain number of radians. Okay, exactly like slope. Perfect, direct chat person. Yeah, exactly. Exactly. I'm saying then that in this case, pi over 2 radians per meter would be the slope, as direct chat person just very wisely said, would be the slope of a phase, of a phi x graph. That's correct. And that graph would be a straight line. Like the slope would be a constant. So then what we said last time is fine. There's nothing special about pi over 2. Pi over 2 is just the easiest one to picture. What we can make this arrangement with any step size we want. And that step size, whatever size we would pick, would be measured in radians per meter. Let's from now on call that step size, that radians per meter, that increase in that amount by which we're staggering the phases as we walk along the x-axis, we'll call that K, a new K with serifs, call that K, and we'll and literally K is called, or stands, well, K is called, and the angular, why angular? Because it's radians per something, but instead of angular frequency, like omega was angular frequency, radians per second. This one is radians per meter. It's called angular wave number. Why is it called? And this is like from lab 3, okay? I'm saying now, omega is so this is getting bad, but angular wave number K is measured in radians per meter, just analogous to how omega, angular frequency, this is totally illegible, I realize. And in principle, everything I'm saying right now in principle was said last Wednesday. And in principle, I'm just trying to review or clarify this. But angular frequency was measured in radians per second. Now, remember again, but so there's these two constants now in this new equation. We've just written this new equation. I'm saying this new equation, y equals a cosine omega t plus kx, can capture this whole package now, right? This one equation can capture an entire horizontal collection of identical phase staggered vertical oscillators, right? I'm saying if you take a bunch of vertical oscillators and you stretch them out along a horizontal axis, if you, not just one oscillator, but multiple oscillators, all staggered in phase by a constant amount, you can capture that entire package, or you can discuss, identify that entire package with one equation that says y equals a cosine omega t plus kx, where k stands for that step in phase, where omega stands for that rate in time. They're both called angular anythings because they have to do with radians, and they both have to do with radians because they're both measuring portions of a cycle, right? So we're now saying we could capture that entire arrangement with one equation that has two constants and two independent, well, actually 3 constants if you include a, and 2 independent variables, t and x. This one equation now says, okay, if anybody walks in the room and wants to know how high mass is, we would say to that person, how high is mass? Well, you got to be more specific than that, we would say. You want to know how high mass is in my big arrangement of oscillating, in my big collection of multiple oscillators? You want to know how high mass is? Well, you got to tell me 2 things. You got to tell me when you're looking, like how high is mass now, or how high is mass later? And you got to tell me where you're looking. How high is it? Because at any given moment, more than one mass is at more than one different height. And if you, so at any given moment, various x masses are at various heights. And also at any given x that I look, the height is changing with respect to time, right? So height of mass is a function both of time and of horizontal space. And that number K, that step by which we're staggering the oscillators in phase, is called angular wave number, because if you step back and look at this arrangement, if we actually made this arrangement, if we took a collection of identical oscillators and staggered them in phase and let them all go, what we would see is crests and troughs rippling back and forth along this x-axis. We would see wave pulses propagating from one end of this x-axis to the other, right? What I'm trying to say with all this is this statement down here, this y function of x and t, is on the one hand a collection of phase staggered oscillators. But on the other hand, it's a wave pulse. A wave pulse is a collection of phase staggered oscillators. In lecture, I'm trying to build up a wave pulse this way. In lecture, I'm trying to tell you, I'm trying to say all oscillator is not a wave pulse. And a cosine wiggle is not a wave pulse. Something that goes up and down cosinusoidally in time is not a wave pulse. And a drawing or some shape that's going up and down cosinusoidally in space is not a wave pulse. But put the two together and you have a wave pulse. In other words, if you have a bunch, if you have something that's oscillating in time and you duplicate it, replicate it, make a whole bunch of it spread out in space and have something that's going up and down in time, spread something that's going up and down cosinusoidally in time, and then spread it out cosinusoidally in space, then you have a wave pulse. Or put the other way, if you draw a wiggle, just a cosine graph, if you just look at a wiggle, that's not a wave pulse. That's just a wiggle. If you just look at a snapshot of a cosine graph, that's not a wave. That's just a cosine graph. But if it starts wiggling up and down in time, then it's a wave. A wave is oscillations in time at the same time as oscillations in space. A wave pulse is cosines in time superposed onto or with cosines in space. One without the other is just one without the other. Both together is a wave pulse. That's what I'm trying to say in lecture. You saw that from the backwards perspective, from the exact opposite perspective in lab 3. In lab 3, you looked at a wave pulse, right? You made wave pulses that went back and forth along this one-dimensional springy medium in the lab. You sent pulses going back and forth. You took a movie of the pulse, then you dissected that movie, or you analyzed that movie. You broke it down into two different sets of data, two different sets of relationship. You took that movie and you looked at in one part of your lab, you picked any given X position and you made red dots. Like you picked an X position in your movie and you watched as the spring went up and down an axis at that X position. You made dots that translated into a graph of height as a function of time, right? In other words, in part of lab 3, you took a wave pulse and you dissected it down to looking at just one little piece of it. And what did you find? A little oscillator, an individual cosinusoidal harmonic oscillator. Then, which is what I'm saying here, like one of these. Then in the other part of your brain or in the other part of the lab, you took a snapshot from your movie, right? You picked a t value. You picked a t value and you just let your eyes gaze along the x-axis. You made red dots and you asked yourself, for some given t value, what is y, like how is height varying as I let my eyes gaze along the x-axis of this one snapshot? So first you picked an x and you looked at y versus t and you got a cosine. Then you looked at some t, some snapshot, and you looked at y versus x and you got a cosine, right? So in lab 3, you took a wave pulse and broke it down and found that that wave pulse consists of cosines in time and cosines, like cosines as a function of t and cosines as a function of x. They're superposed. They're happening together as one phenomenon. All of that data is being taken from one movie. So the whole thing is a cosine of time and space. In lab 3, you're saying, let's look at a wave pulse and break it down. Oh, a wave pulse is simultaneous but independent, superposed cosines, harmonic oscillations in time and in space. That's what lab 3 is saying. I'm saying in lecture, I'm going the other way and saying, what if we build a bunch of oscillators and spread them out in space? What we would get is cosine omega t plus kx. We would get a wave pulse. I'm trying to say, and then I'm going to move on. But what I'm trying to say right now, if I say nothing else, I will say other things. I'm trying to say right now, we started this whole, we've spent a long time analyzing harmonic oscillation because it's a fundamental ingredient. to what we're building now. We looked at harmonic oscillation of an individual oscillator, and we kept saying it could be described as A cosine omega t, A cosine omega, or X naught cosine omega t, or whatever. Cosine omega t, that's an oscillator, that's an oscillator. Then we eventually expanded our horizon and said we could have more than one oscillator. So it could be, so any individual one could be described as omega t plus a number, call it phi. Then now I'm saying, if we make a whole collection of oscillators, we have a whole bunch, and they're all organized so that their phases are not just individual random number, but their phases are actually in a pattern. Their phases are actually a function of where they are. Then we can package the whole thing and say, aha, y equals a cosine of omega t plus kx. This is a wave pulse. A wave pulse is a collection of phase staggered oscillators. A wave pulse is harmonic oscillations happening in time while superposed on harmonic oscillations happening in space. Or if you like, harmonic oscillation in space, harmonically oscillating in time. It's both is what a wave pulse is. And it's described by that one equation, y equals a cosine omega t plus kx. That's where we are. Technically, everything I just said is old. I mean, technically, it's just a recap of lab 3 and what I said in lecture last time. But that's where we are now. Okay, oh, sorry. Yeah, is this too? Yes, the one in space. Yes, very good, John. I told the one in space is the still one, the one where we just pick a value of time. That's correct. Exactly what John said. Yeah, that's good. Oh, and let me see this also. This track I'm looking. Yes, right. I think I agree with it. Yes, yes. Like, yeah, to both of you. I mean, to John and to Maisha. Like, I mean, and to everybody, obviously. Like when I keep saying that it's a superposition, or it's time oscillations superposed onto space. Oh, wait, okay, that's great, Elizabeth, with an S. That's totally, I mean, all three of you, great, great. But yes, I totally want to dwell. I do need to dwell on the thing that Elizabeth with an S just said. I don't know why I always say Elizabeth, because the other one's Lizzie. I don't know why. But anyway, let me just like quickly wrap up my like addressing of what John and Maisha are saying, because it's very good. And then yeah. But yes, this is all about unthinking things ultimately. Like, we've spent many weeks analyzing the exact math or physics of a thingy thing, like oscillating harmonically. And now what I'm ultimately saying is we needed to do all that because we need to put a bunch of thingy oscillators together in order to ultimately make an unthingy thing. That is right. That is the point of this. And on the John Maisha thing, I'm saying, yes, part of the way we see that. Well, I think, did I write this down? Well, part of the way we see that is we realize in lab 3 that one thing, you can hold one thing constant to look at how the other thing is varying, or then you can hold that thing constant to see how in other words, in lab 3, you can pick one value of X, hold it constant, just pick a position, like somewhere along that stretch of spring, just pick a horizontal value and track and put a red dot wherever the spring is, wherever the height of the spring is there at that horizontal place. And then you put that red dot there, and then the frame advances in your movie. So now you're still looking at the same X spot, but you're asking, how high is the spring now? So you put a new red dot, and then the movie advances again. So now you're asking again, at that X value, where's the new height? So there you're holding X constant and asking how Y varies as a function of T. But conversely, you can, so that's the Maisha thing, or you could do the John thing of holding T constant, just picking some moment in time, some frame from your movie, and varying X, letting your eyes wander along the X axis and ask what's happening to the height as a function of X. So you can do one or do the other because they're both happening independently of each other, but they're both happening at the same time. So the result is a superposition. The result is the whole being a sum of its independent yet simultaneous parts. And that's what I really do mean by superposition. A sum of simultaneous yet independent parts. Like they're not affecting each other. They're just contributing to the whole. So yes, that's what we did. And yes, what we get is unthingy things. Now that's why I want to develop that even further. Now, let me just go back to the notes. So, all right, so we had this, we had that. Okay, so yes, on to this unthingy implication. Here's what I'm saying. That y equals a cosine omega t plus kx, like that's a description now of a pulse, a wave pulse propagating along a one-dimensional medium. So what do I mean by propagating and what do I mean by medium? One-dimensional, like we're talking about, like that all of this was happening like on your long slinky, that your lab partner held one end and you held the other, or whatever, right? As opposed to like what this equation here is like about waves propagating along a one-dimensional medium, as opposed to like waves on the surface of the ocean. Those are waves too. And this math ultimately totally applies to that as well. But waves on the surface of the ocean are like waves on a surface on a two, like they go up and down, but in the X, Y plane. So that's like one step more spatially sophisticated. We're talking here about pulses propagating back and forth along a line. Now, what do I mean by propagate? By propagate, I literally just mean travel. That's all propagate means, travel, move. But it is the word that we deliberately use whenever we're talking about an immaterial entity, i.e. an unthingy thing. Like we say baseballs travel, or planets travel, or cannonballs travel, but wave pulses propagate. A wave pulse is ultimately immaterial. It is unthingy. Let me be and that's a huge point. Like I'm glad at least two people made it in the chat. Huge connection, observation on your part. It's really the purpose of this course. We started off the course like looking at unthingy versus thingy. And then we got so caught up in all of this math and all these specific examples of a damn thing going up and down a spring. And I'm sure many of you, I mean, including me, were like, oh my God, what is that? I need this, like, where's this heading? Where it's heading was to today. Like a mass on a spring is a thingy thing. It's a material, particular, massive object that's like moving up and down. It's traveling up and down. But you put a whole bunch of them together and so in a very precise, intricate way. And next thing you know, you have something immaterial moving. What do I mean by that? I literally mean it says here on the board, when a wave pulse propagates from location A to location B, no identifiable particle needs to travel from A to B. That's an enormous point. Let me pause on that for a second. Like really, and I mean, I never get sick of saying, I said this 400 times already this morning, and I'm going to say it to the other class. Now I'm going to happily say it 400 times to you again, and for the rest of the semester, because it's such a crazy point. This is what I mean. I mean, when you did lab 3, when you stood on one end of your slinky and the other person stood on the other end, and you just did this very simple, like not hard thing. You just like shake, like you shook your, and you saw this crest, like bubble or pulse or however you want to say, sort of travel across to your partner. You saw something real, like a crest, right? Like a bump in your slinky absolutely moved from you to your partner. Maybe you sent many of them. Maybe many of them moved. Maybe they moved in succession. Maybe they moved to your partner and then started coming back. Like all kinds of patterns might have happened. But let's just talk about one for a moment. You shake your string and this little bump, this little disturbance, this little shape in the spring propagates from you to your partner. Now, first of all, you see it with your eyes. It's real. Second of all, you could totally measure it, right? Like you could literally measure like, okay, my partner is 5 meters away from me. And I say, go, and someone's going to start a stopwatch right when the bump leaves my side of the room. And I'm going to tell someone else, like my third lab partner, to stop their stopwatch as soon as the bump gets to my other partner. And we won't do it perfectly. We don't do anything perfectly, but we'll all basically agree on what we're talking about. And we'll all know to start the stopwatch when the bump leaves me and stop the stopwatch when the bump like lands at the other partner. And again, we won't do it perfectly, but you know we're doing something meaningful and real, because if you really screw it up, someone's going to yell at you, right? Like if you start your stopwatch and then you just like aren't paying attention at all, and you just like stop your stopwatch, like when the bump is like halfway across, people are going to go like, no, dude, you stopped too early. Like what? Like everybody knows what we're talking about. You stop the stopwatch when the bump gets to your partner. Again, are you going to stop your stopwatch perfectly? No, but if we were doing this with a baseball, you wouldn't stop your stopwatch perfectly then either. But we would all know what we were talking about. And what I'm getting at is this. Your partner is, say 5 meters away from you. The bump will take like, say, 10 seconds to get, or whatever, 2.5 seconds to get to your partner, right? So then we could take that distance and we could divide by that time. And we could say, oh, it took that bump took 2.5. It was traveling at a velocity of 2.5 meters per second. And we'd be right to say that. We wouldn't be perfect, but we would be totally meaningful in saying that. So meaningful that then we could make a prediction. We could be like, okay, I bet if we get 10 meters apart, me and my partner, I guess it'll take the whole bump like 5 seconds to get to my partner. Like we could make a prediction using that velocity the same way we would with a baseball. What I'm getting at here is that something clearly moved from you and your partner that we didn't just all notice and observe. Like we did observe and notice it. It was real. It was in the external world, but also we can make a measurement of it. We can analyze it, put that measurement into equations and make a prediction of it. And we'd be right in our predictions. Like something scientifically legitimate occurred when that bump left you and went to your partner. A motion that was measurable, analyzable, and predictable occurred in the real world, right? Furthermore, and that, I'm not saying that's crazy, like that's just true. But then furthermore, like we would say, like, okay, a motion occurred for me and my partner. Like what motion occurred? Well, little pieces of metal moved. In fact, if you really think about all the math that I'm trying to say here, we all understand like a little piece of metal over here on your side moved up and then it moved down. And then a piece of metal next to it moved up and moved down. And a piece of metal next to it moved up and then down. In other words, you had a collection of phase staggered oscillators in effect. Like you saw something move from you to your partner. You can measure it, analyze it, and predict it. A motion occurred. And if you ask what moved, the answer is metal. Metal moved. Okay, so what's the problem, Yaverbound? Like, why am I getting so excited about this? Because motion occurred from you to your partner, from location A, you, to location B, your partner. And the thing that was moving was definitively, undeniably, and only metal, right? Yet, no piece of metal ever went from you to your partner. That is my point. That is a big point. Let me say that again. Motion occurred scientifically, measurably, analyzably, predictably. Motion occurred. That's point one. Point two, the thing that was doing the motion was, actually, I'm sorry, no, let me say it better. Motion occurred from you to your partner. Something moved from you to your partner. Number two, the only thing that was ever moving was metal. Point number three, no metal ever went from you to your partner. And I'm going to look in the chat in 1 second. But therefore, what I'm saying, and it's such a simple, elegant like point, but it's such a big point. I'm saying that what moved from you to your partner was immaterial. What moved was a disturbance in the metal, a shape of the metal, a deformity. What moved was only metal, but no metal ever did that journey. What did that journey was some shaping of the metal, some organization of the metal, not the metal, but organization itself, or shape itself, or energy, if you like, itself. I would ultimately say information is what moved from you to your partner. Whatever moved from you, well, what we're ultimately calling it is a wave pulse. But I'm saying here and now, what a wave pulse is a type of motion that is analyzable by all of our normal methods of physics motion analysis. And it's a type of motion that occurs in a meaningful way in the material world, but is itself not material. I'm agreeing, in other words, with Elizabeth, who said this is unthingy motion at its best, at its most vivid. This is unthingy motion, and yet somehow we can mathematically analyze it, and that's what here to do. This is unthingy, immaterial motion. This is motion that matters, but isn't made of matter. This is motion that is a difference that makes a difference. You see what I mean? Oh, I'll say it the other way again. It's motion that matters, but it's not matter. And lastly, and I'm sorry, I know there's something going on in the chat. I will look in the chat in a second. But so I'm saying propagate is the word we use to describe motion of immaterial things such as wave pulses. And medium, written on the side here, what the medium is the collection of material particles that are oscillating to allow this to happen. Like a wave pulse moved through the metal from you to your partner. Metal did not move from you to your partner, but metal was needed. A bunch of metal was needed to oscillate all in this pattern of patterns, right? Each little bit of metal was oscillating in a pattern, and they were all organized in a pattern of those patterns. We needed material objects to do that in order to create this pulse. The collection of material particles that are all oscillating in this phase staggered fashion, that collection of material particles through which the pulse propagates and without which the pulse would not be possible, that collection is called the medium. So the medium is not something that gets in the way of the wave pulse. It's something that allows the motion of the wave pulse. It's necessary for the wave pulse. That's what the medium is. A wave pulse is immaterial motion. The medium is the material that allows for that immaterial motion. Let me pause for a second and look in the chat, and then I'm going to keep going with the math. I'm looking at the time. Oh, it's almost 4 o'clock. I see that now. Maybe that's what's in the chat, but I do want to, okay. Right, exactly what John said in the chat. The metal did not travel. It's just a bunch of little pieces of metal all moved in a pattern. That's exactly right. And I might even go so far. Yeah. Exactly, Elizabeth with that. Awesome. Yeah. So the spring, in the case of lab 3, and carrot thingy agreement, yes. In the case of lab 3, that spring is the medium. Let me also take this one step further at the risk of taking this one step further. Like, you know, those pulses along the spring are like the most vivid example to look at them. And that's why we spent all of lab 3 analyzing it. But, you know, right now I'm shouting and you're hearing. Right now I'm sending something from my mouth to your ears. Well, and granted through the internet and all that, but forget the internet for a minute. Like imagine we're in the same room and I'm shouting and you're hearing me. What's happening? I'm oscillating little air molecules. Air molecules are oscillating back and forth. Then air molecules next to them are oscillating back and forth. Air molecules next to them are oscillating back and forth. So we have this big pattern of patterned air molecule motions. The only thing that's moving when I'm yelling at you right now is air molecules. But no air molecule is going from my mouth to your ear. I freaking hope, right? Like, and then you know, like I'm not sending air to you. I'm sending a ripple through the air to you. And if the air weren't there and we didn't have water or anything between us at all, if we were in outer space, right? Like if we were in outer space, you wouldn't be hearing me, is what I'm saying, because you got to have a medium through which the medium doesn't get in the way of the pulse. The medium provides for the pulse. If we didn't have a medium, if we were in outer space, literally, you would not hear me right now because there's nothing to, you can't have a wiggle without something wiggling. Okay, so now I know we're going to wrap up soon. I promise that, and we will soon. But I want to do a little math here. What we have now to describe this pulse, we have y equals a cosine omega t plus kx. That is now, for the first time ever in our lives, that is a function of 2 independent variables, t and x. In the lab, and they're literally 2 independent variables. Not only are there 2 of them, but they're independent of each other. Whatever's happening in the t is not affecting what's happening in the x, and vice versa. So y is a function of t while it is also a function of x. What you did in the lab is you sort of broke that phenomenon apart into its 2 dependencies. That's what you did in the lab. Mathematically, we can do that as well. Mathematically, we can look at how y changes, how y, yes, no, thank you. You're right, it is. I'm gonna go a little, it's totally 4, and I was so polite to do in the direct chat, so I shouldn't be calling attention. But yes, it is 4. I'm gonna start wrapping up. I'm not like letting you go like right now, folks. I'm gonna start converging this, but I might even go as late as 4:10, but which is late for me being early, but it would still be early. Like, so bear with me. But I apologize. Yes, I appreciate it. I might even go to, but anyway, okay. So I'm saying, just like you experimentally did in the lab, you can mathematically take a function of more than one variable, and you can look at how the dependent variable rises, how it rises per run. And what we can say is how much a dependent variable rises, like even if we were to make graphs or whatever, well, you did make graphs. If you want to look at how much infinitesimally a function rises along the dependent axis, it would be, as long as these two independent variables are literally independent of each other, then the amount that something rises in total would be the sum of how much it rises in relation to one of the independent variables plus how much it rises due to the other contributing independent variable. In other words, we could say that the derivative of a multivariable function is the sum of its individual partial derivatives. I'm going to turn the page 1 second, but I'm saying this is a new concept. I'm not expecting you to know this. I am telling you that the amount that a multivariable function rises is the sum of how much it rises due to one variable plus how much it rises due to the other variable. And these individual contributing rises or rises per runs, we can call partial derivatives. And they are designated with, instead of a regular d, a funny squiggly d that kind of looks like a lowercase delta. And this is what I'm saying on the next page. I'm saying we have y equals a cosine omega t plus kx. That is now a function of two variables, x and t, right? That's what I'm saying here. And again, I am aware of the time, and bear with me. I don't want to get anybody's hopes too up, and I will say too, when I finish, whenever it is in a few minutes, I won't be able to answer questions today. I apologize. I just have to run. So please, if you have any questions, like jot them down and remind me, or text me or email me, or just tell me right at the beginning of class on Wednesday. Okay, I apologize in advance, but when I say we're done, I'm just going to run. But anyway, I'm saying here, this is a math concept, that whenever you have a function of more than one variable, the rise in the dependent variable is the sum of its individual contributions to rise. Each one of these things here, this is called a partial derivative. That funny symbol. This would be the partial derivative. The first one would be partial derivative of y with respect to t. The other one would be partial derivative of y with respect to x. Again, if nothing else, even if I get cut off right now, I'm not writing down something that I think you already know. This is not a reminder. This is a new assertion. I am saying that this is the mathematical symbology of what you already believed in the lab, that you can separate independent parts and put them together at the end of the day. So superposition, if y is a function of t and x independently, then the differential rise in y is the sum of its partial differential rises. That's what this says. So what does this really, and I am watching the time, what does this mean to us on a practical level? It means we can take that function y equals a cosine omega t plus kx. I'm going to do this fast now. We can take its derivative, we can take partial derivatives, just like you did in the lab. And just like Maisha and John were saying before Elizabeth said the thing about unthingy thing, we can differentiate that function with respect to t by, in our mind, treating x as a constant. Just like you did in the lab, we can hold x as a constant, just pick an x value and treat t as a variable and take a partial derivative with respect to t. Similarly, we can hold t constant and take derivatives with respect to x. If we do that, we get what's written right here. Now, you may have to write this down and you may have to think about this in your own time in the next few days. I encourage you to. It's not hard, but you just might have to think. I'm saying the partial derivative of that function y with respect to t equals negative a omega sine omega t plus kx. I just took the derivative with respect to t. I pretended like I acted like x was a constant. It's not really. but I held it constant for a moment because I'm just asking, when I walk a little bit on the t-axis, what happens to y? Literally, again, it's just what you did in lab 3. It's just saying, if you pick some x value, how does y vary in response to t? So then I took the derivative again. So I got partial 2y, partial t squared. I am looking at the time. Okay, it's not bad. I took it again, and I got negative a omega squared cosine omega t plus kx. That might not even be a surprise to you. It might look like old familiar. It is pretty familiar. It's just taking two derivatives of that function with respect to t. It's pretending x is a constant. But then in the next part of the page, then I switched and said, now this is like me just looking at a snapshot now. What if I just take partial of y with respect to x? What if I treat x like it's the constant? And what if I treat x like it's the variable and I treat t like it's a constant, right? Then same logic applies, like chain rule and trigonometric derivatives. But now if x is the variable, then k will come out from the chain rule, right? And omega and t won't come out because they're like a constant now if I'm doing partial y, partial x. You see what I'm saying? So I'm saying this is allowed in math. Again, please understand, I will leave soon, but please understand, I'm teaching you this now. Please don't look at your notes later and be like, wait, where did this come? I mean, is he assuming that I know about partial derivatives? No, I'm explaining partial derivatives. I'm saying we're allowed, we now for the first time in our lives have a function that varies with respect to two variables that are independent of each other. The two independent variables are t and x. We can take derivatives one part at a time. And when we do that, we use these funny new deltas to mean partial derivative. So the second partial derivative of y with respect to t is negative a omega squared cosine omega t plus kx. The second partial derivative with respect to x is negative a k squared cosine omega t x. And then I say, and we're almost done, I promise. Thank you for your patience. Then I say, oh, that's interesting. The second partial derivative with respect to t kind of looks very similar to the second partial derivative with respect to x. Like they both have that same cosine term in them. So I can rewrite, you might have to put these steps in your notes. I just rearranged. I took the second partial derivative and I divided, I rewrote each one to just get cosine by itself. I'm saying and then I set equal to each other, right? So I got this by itself and I got this by itself. How did I do that? I divided both sides, I divided both sides by that, and I divided both sides by that. And then I set them equal to each other because if two things are equal to a third, then they're both equal to each other. If A equals C and B equals C, then A equals B. So if cosine equals partial 2y over partial t squared over negative a omega squared, and if cosine also equals partial 2y over partial x squared over negative a k squared, then they're equal to each other. So I set them equal to each other down here at the bottom of the page. I promise so I got partial 2y partial t squared over negative a omega squared equals partial 2y partial x squared over negative a k squared. So the a's cancel out, like I divide both sides by a. The negative ones cancel out, I divide both sides by -1. And what I get, and we're going to end here, what I get then is this thing, partial 2y partial t squared equals omega squared over k squared, or in other words, omega over k squared times partial 2y partial x squared. That looks like a freaking mouthful, I would imagine. That may be the most exotic equations you've ever gotten yet in physics, but you are capable of understanding every single piece in it. We've been building to this point. We've been setting out all these pieces so that we could put them together and have this package. This is the wave equation. Anything that looks like a wave, a one-dimensional wave, must be describable by this. And anything that is describable by this is a one-dimensional wave. It is our second order differential equation in this class. Our first differential equation was this one, Hooke's law for an individual oscillator. This looks a lot like that. If you really stare at them for a while, you'll see it's very, very, very similar to Hooke's law. In fact, it's really the same thing on the left side. And then on the right side, there's a constant, just like Hooke's law. The only big difference is that Hooke's law says second order derivative equals some constant times variable. This says second order derivative equals some constant times derivative. It's one step more exotic, but we will unpack that. We will unpack that more on Wednesday. I'll explain, believe me, I'll explain it. I'll show you how to apply it. I'll show you what, but what I'm saying right now is this is the wave equation. This describes anything that is a wave, and anything that's a wave must be described by this. So I'm going to stop there. Thank you for being so patient. We'll pick up on this on Wednesday. Oh, thank you. Have a great night. Thank you, guys. Have a great night. Thank you for being so patient and everything. Awesome. Oh yeah. And yeah. Okay. Thank you. Okay. Thank you, guys. Okay. Thank you, guys. Okay. So I'm going to stop.